Statistical machine learning has one strict objective: generalization. The goal is never to build an algorithm that perfectly memorizes the dataset it has already seen. Instead, the model must extract underlying patterns to accurately predict unobserved future instances. Imagine a two-dimensional feature space populated with noisy, scattered data points. Building a model means finding a mathematical decision boundary, defined as Wx minus b equals 0, to neatly separate these clusters. To evaluate how well that boundary fits, we calculate empirical risk, or average loss. Using the squared error formula, we measure the penalty for misclassifying the training data. We take the difference between the predicted value and the actual value, square it to heavily penalize larger mistakes, and average that penalty across all n instances. It is tempting to force this empirical risk all the way down to 0. But blindly minimizing loss on your training data leads to a critical failure when that model is deployed in the real world. This creates a strict divide between training error, how well the model performs on seen data, and test error, which measures performance on new, out-of-sample data. The numerical gap between these two metrics determines the true value of a model. Achieving zero empirical loss is functionally useless if the model's predictions collapse the moment it encounters fresh data. To survive the reality of unobserved variables, a machine learning engineer must strictly govern the mathematical complexity of the model itself. To see how mathematical complexity dictates performance, we use polynomial regression to test different degrees of complexity against a single dataset. This chart shows 3 polynomials fit to the exact same data points. Look at the horizontal dashed line. This represents a degree 0, or constant, polynomial. Because the mathematics are too simplistic, it entirely fails to capture the upward structural trend of the data points. This state is called underfitting. Now look at the red dotted line, a degree 9 polynomial. By granting the model excessive degrees of freedom, we allow it to perfectly intersect every single training point. But the result is wildly erratic, spiking aggressively between the known values. The complex model is absorbing the sampling noise specific to this dataset. It is treating random chance artifacts as if they were true structural signals. The optimal generalization is found with the solid green line, the degree 1 polynomial. It strikes a strict compromise between simplicity and structural accuracy, passing cleanly through the center of the data distribution. Model complexity dictates a critical divergence. A model will either fail to extract the true signal, or it will hallucinate complex patterns in random noise. This tension is formalized in a specific decomposition theorem. Generalization error is the exact mathematical sum of 3 components: bias, variance, and irreducible error. This diagram shows predictions aimed at a target variable. Look at the leftmost target diagram to understand bias. Bias is the error introduced by erroneous baseline assumptions. If you assume a curved relationship is perfectly linear, your predictions might be tightly clustered, but they will be systematically off-center from the bullseye. Variance, shown in the rightmost diagram, measures the model's hypersensitivity to small fluctuations in your training sample. If resampling your training data yields wildly different models, causing predictions to scatter widely across the board, your variance is high. The third component, irreducible error, represents the inherent noise within the data source itself. Whether from broken sensors or unmeasured variables, no algorithm eliminates this. The remaining 2 variables are locked in an immutable trade-off. Increasing a model's complexity drastically drops its bias, but simultaneously balloons its variance. Engineers cannot fully eliminate predictive error. They can only choose which type of error they are willing to accept by consciously trading bias for variance. Theoretical trade-offs are useless without empirical measurement. To verify complexity in practice, models are tested against isolated holdout validation sets. We track this testing using a learning curve. This plots a model's training error and validation error as a function of the total amount of data it has been fed over time. This graph shows the learning curve of an underfitting model with high bias. These 2 lines, representing training and validation errors, quickly converge, locking together at a very high plateau on the y-axis. When curves plateau at a high error rate, adding more training data is mathematically futile. To drop the error, the engineer must supply more informative features or upgrade to a more complex model. This second graph shows the curve of an overfitting model with high variance. Notice the exceptionally low training error on the bottom line, paired with a massive, persistent physical gap before reaching the validation error curve above it. High variance demands a different intervention. You must either feed the model more data to close that gap or aggressively constrain its mathematical complexity. Learning hurts are the definitive empirical proof of a model's structural integrity. They reveal if complexity aligns with the actual reality of the data. This presents the final engineering challenge. How do we successfully manipulate this complexity trade-off when building real systems? The first method is regularization. By artificially constraining a model and reducing its degrees of freedom, we intentionally inject a small amount of bias. In return, we achieve a massive, stabilizing drop in variance. A second method is ensemble learning. This diagram illustrates bagging and bootstrapping, splitting data into random samples fed into parallel predictors. By averaging their predictions together into a single output, we mathematically halve the overall variance without increasing baseline bias. Generalization error is an inescapable physical limit. Viewing empirical risk in isolation is a mathematical trap, and the bias-variance trade-off dictates all model architecture. The ultimate mark of a skilled machine learning engineer is not the ability to force training loss to zero, but the statistical discipline required to expertly tune complexity to survive out-of-sample realities.